Hey class, this is screencast for the notes for 15.3 and 15.4. So we're talking about the K value. So what does the value of K actually mean? Well, there is one situation where of course we expect K to be very large, and that is when we have like our typical chemical reaction where we put something together and we expect it to go like maybe something as easy as burning natural gas, and we expect that reaction to go very far to the right, which means that we're going to put these two together, the methane and the O2, and it's going to produce my two products of carbon dioxide and water, and we expect that to happen almost completely to the right hand side. So there's going to be very little O2 and CO2 and CH4 being made, yet we're going to have everything on the right hand side in plenty. That's going to give us a K value that looks something like this, where we have lots of products and very little reactants, almost no reactants. Okay, so when that happens, that's called a product favored, or products predominate at equilibrium. Okay, a products favored reaction. Many of the reactions that we talk about up till this point actually do favor the products. And that's because we're producing something new, which is kind of the point of chemical reactions. But they don't all do that. So sometimes you put reactants together and you get very little product. You still get some, but very little. So if K is much larger than 1, that means that products are favored. If K is much smaller than 1, that means the reactants are favored. Okay, so this is actually pretty obvious, but when you look at a K value for a reaction, you can tell whether the products are favored or the reactants are favored. So we take a look at our example from before. With the equilibrium constant of a reaction, the reverse reaction is reciprocal of the equilibrium constant. So you take a look at this and we talk about the reciprocal. So the forward reaction goes from N2O4 to 2NO2. That would give us a products over reactants. You know that 2 comes from the 2 that you see here in the coefficient for NO2, and that gives us a 0.212 at 100 degrees Celsius. Okay, now also, if we're looking at the reverse reaction, notice that the Kc for that puts the N2O4 on top as a product and the NO2 squared as a reactant. And notice that's 1 over 0.212, which gives us 4.72. So if we're talking about the forward reaction of this one again, okay, the N2O4, is this a products favored or a reactants favored? Okay, well, K is not very large or very small. Something very small might look like 1.0 times 10 to the negative like 18. That would be very, very small. That would be for a K value. If K equals this, that would be like putting a rock in water and having the rock change very little, because the K value is very small, which means the reactants stay basically the way they are, and the products are hardly ever produced or hardly produced at all. Okay, so this is very close to the R1 value. So I would say that the reactants are favored, but not very much. Okay, let's continue on here. So manipulating equilibrium constants, the equilibrium constant of a reaction that has been multiplied by the number is the equilibrium constant raised to a power. That is equal to the number. So in other words, if we are multiplying the concentrations or the amounts of the reactants and products, we are putting the K, for the K value, we're putting those concentrations up by that exponent, okay? Or you take the 0.212 squared. That's what happens when you double an equation. So when you double an equation so that you have twice the number of dinitrogen tetroxide, or N2O2, or N2O4, I mean, when you double that number and you double the amount of product of 4O2, of 4NO2, then what you do is you raise those to the exponents. And that's what happens to the Kc then. Kc then is raised to an exponent. Okay, so that's good to know because we're going to use that in our problem sets that we have coming up. So manipulating the equation, okay, let me just take a look at this. The equilibrium constant for a net reaction made up of two or more steps, the product of the equilibrium constants for the individual steps. So that means, and let me just see, okay, nope. Okay, for this, don't write this down. I'm going to show you exactly what that means in problem 24 for the problem set that's due this coming week here, for this week. So I'll get to that. This is problem 24. Take a look at the screencast for those problems to understand exactly what the equilibrium constant for a net reaction made up for blah, blah, blah means. So heterogeneous equilibrium. So let's talk about concentrations of solids and liquids. They are essentially constant. So when you have something that looks like this, I got PbCl like this, and then over here I get Pb with a +2, and that's aqueous because that's dissolved in water, and I get Cl, I should put a 2 in front here, Cl minus like this, and that's dissolving lead chloride, lead 2 chloride. So when you're dissolving lead 2 chloride, your products are going to be the ions that you see over here. Now, when we talk about the actual solid though, the actual solid here, the concentration of this solid does not change. Remember, concentration is like the number of moles per liter. So if we're talking about an actual solid, a pure solid or a pure liquid, the concentration is essentially 1. It's 100% the solid. And that concentration doesn't change at all. So even if you have the smallest amount of that solid left, that concentration of the solid is still 1. But the more solid that dissolves, like the higher the concentrations, obviously over on the other side of the Pb +2 and the Cl -1. But the concentration of the solid doesn't change. So the concentration is like a ratio, and for a solid, it is essentially 100% if that solid is present at all. That's true for liquids too. So when we talk about water, like a neutralization reaction where we're producing water as a product, that's a liquid, and it will not change in concentration. The concentration of water will always be 1.0. Not 1 molar, it will be 100%, which means we're multiplying just by 1, which we don't have to worry about. So that means that when we look at, and here's my example, when we look at a Kc, we do not have to consider pure liquids and pure solids. We do not put them into the equation because this is products over reactants, and this would be essentially putting our products over a reactant of a concentration of 100% or 1. And that will not change either. So if this doesn't change and it's always these two products divided by 1, why even put them in there? So we don't have to worry about putting in solids and liquids. But that means that you have to remember to exclude this on the Kc or the equilibrium constant expression. Okay, let's keep going. As long as okay, so we have another example here. Here is calcium carbonate. As long as some calcium carbonate or calcium oxide remains in the system, the amount of CO2 above the solid will remain the same. So as long as we have these two solids present to establish an equilibrium, then the CO2 will remain present also, even if we change the amount of mass of CaO and CaCO3, of calcium oxide and calcium carbonate. Even if we change those masses, the amount of CO2 should not change, or the pressure of CO2 should not change, because as long as we have some amounts there, we're going to establish the same equilibrium, where the CO2 wouldn't change then also. Okay, sometimes that's a little tough to get your head around as far as equilibrium is concerned. Okay, we're not going to do any more with equilibrium calculations. I'm going to show you examples. We're going to do AP problems this coming week. So, hang tight for that. That's it for 15.3 and 15.4.